свои процессы, да? Чтобы зависало?
Нет, чтобы потом...
Чтобы потом проще было, ну да. Okay, today our first goal will be to discuss some spectral properties of system algebras and to deduce a rather simple but important result, namely the Eagle-Dynamic theorem, which is in fact lies in the foundations of system algebra theory, and which states that for any cumulative system algebra, the Gelfand transform is an isometric star isomorphism onto the algebra of continuous and vanishing at infinity functions on the spectrum. Well, let's start by looking at some spectral properties of system algebras. First of all, let's introduce some terminology. Suppose that A is a star algebra. At this point, we don't assume that it carries a norm, so just a star algebra. And it lays an element in A. Then we say that A is self-adjoint. If it is self-adjoint, if A star equals A. So the name is self-explanatory. More generally, we say that A is normal. A is normal if it commutes with A star. Also, if our algebra is unitary, then a natural class of elements is a class of unitary elements. So if A is unital, then we say that an element little u in A is unitary if it is invertible. U is invertible, and the U inverse equals U star. Well, let's make some simple observations related to this definition. First of all, it's clear that every self-adjoint element is normal. Every self-adjoint element is normal. It's clear. And also it's clear that every unitary element is normal, because U and the U inverse definitely commute. So every unitary element is also normal. So normal elements generalize both self-adjoint and unitary elements. Actually, this is one of the main reasons to introduce normal elements. And second observation, which is also quite trivial, but nevertheless it is very important, and we will often use it, is that for every element A in A, the element A star A is self-adjoint. Well, this is clear from the properties of the involution. It's useful to introduce a special notation for the set of all self-adjoint elements. Let's denote the set by A as A. So this is the set of all self-adjoint elements in A. By the way, sometimes self-adjoint elements are called Hermitian. Okay, let's look at some examples. Example 1. Suppose that A is the algebra of functions, of all functions on an arbitrary set X. Or we can take, for example, the algebra of bounded functions on X, greater than infinity of X. Or we can take the algebra CB of X of continuous and bounded functions on a topological space. In all these cases, the involution is just the complex conjugation. So it's clear that an element f of a function f, is self-adjoint, if and only if it is real. If f of x is real for all x. Also, it's clear from the definition that f is a unitary element, even only if the absolute value of f is identically 1 for every x. Well, and of course, all elements of this algebra are normal, because the algebra is commutative. Let's now look at the algebra of bounded operators on a Hilbert space. An example and exercise at the same time. So let A be the algebra B of H of bounded operators on a Hilbert space. Then an operator T on H is self-adjoint if and only if the following number, the inner product of Tx and x, is real for every x in H. So this is function x. Sometimes it is called the quadratic form of T, so it has to be real. This is necessary and sufficient for the self-adjointness of T. And second, an operator U on H is unitary in the sense of this definition, even only if it is bijective. U is bijective and preserves the inner product. The inner product of ux and uy equals the inner product of x and y for all x and y. Well, normally self-adjoint elements can be considered as real elements. So in some sense, they are analogs of real numbers. It's more or less illustrated by these examples. So a function is self-adjoint if and only if it is real, and an operator is self-adjoint if and only if its quadratic form is real. And our next simple proposition emphasizes this analogy between self-adjoint elements and real numbers. So I claim that for every element in A, there is a unique pair of self-adjoint elements, B and C, of self-adjoint elements, such that A equals B plus I, C. So in some sense, B is the real part of A and C is the imaginary part. And the proof is very easy. We can define B and C by explicit formulas. Namely, B is A plus A star over 2, and C is A minus A star over 2i. So clearly, both B and C are self-adjoint, and they satisfy this equation. And also, it's clear why such a pair is unique. Because if A is represented in this form, B plus IC, where B and C are self-adjoint elements, then we can apply the involution and write A star equals B minus IC. And by solving this system of equations in B and C, we deduce that B and C are necessarily given by these formulas. So such a pair is unique. Okay, so let's now, so far A was an arbitrary star algebra. Let's now assume that A is a C-star algebra. Then we have the following important result. This is theorem 1. Suppose that A is a C-star algebra, and nuclei is a normal element of A. I claim that the spectral radius of A is equal to the norm. So let's recall that in the general case, that is in an arbitrary Banach algebra, the spectral radius is always less than or equal to the norm. And sometimes, well, the inequality turns out to be strict. For example, for nilpotent elements, or more generally for quasi-nilpotent elements, we always have a strict inequality. But for normal elements of C-star algebras, these numbers are the same. Well, to begin with, let's consider the case where our element is self-adjoint. If, say, B is a self-adjoint element of A, then by the C-star axiom, we have the following equality. This is just a special case of the C-star axiom. Let's now extend this equality to normal elements. Suppose now that little a is normal. Let's substitute A star A here for B. So A star A squared is the norm of A star A squared. So this is true because A star A is self-adjoint. Well, the left-hand side by the C-star axiom is equal to the norm of A to the power 4. Let's now look at the right-hand side. So this is A star A star A. But the element A is normal, so we can interchange here A and A star. And we have A star squared times A star, or equivalently A squared star times A squared. And again, by applying the C-star axiom, we get that this number is equal to the following one. These two numbers are the same. We take the square root and we deduce that the norm of A squared is equal to the norm of the element A squared. So in other words, this quality holds not only for self-adjoint elements, but also for normal elements. Now we observe that by using induction over n, we can prove the following formula. If we take A to a power which is some power of 2, then we have the following one, the following equality. This is obtained from this one by induction over n. And if we now calculate the spectral radius of A by the Berling-Griffin formula, which is the following limit, so we can take the limit over the subsequence of powers of 2. The limit will be the same. But this equality shows that every element of the sequence is just the normal way. So as a result, the spectral radius is equal to the normal way. Let's now look at some corollaries of this formula. Corollary 1, if A is a C-star algebra, then for every element A in A, the normal way is equal to the square root of the spectral radius of the element A star A. Well, indeed, by the C-star axiom, it is equal to the square root of the norm of A star A, but A star A is self-adjoint, so its norm is equal to its spectral radius. Why is this formula useful? It is useful because the right-hand side of this formula is determined by the algebraic structure of A, so it doesn't involve the norm. The right-hand side is pure algebraic. Therefore, we see, and this is our corollary too, that if A is a star algebra, then there is at most one norm on A, which makes A into a C-star algebra, making A into a C-star algebra. And this norm is given by this formula. Equivalently, this result can be stated as follows. Every star isomorphism between two C-star algebras is isometric. By the way, at the end of the previous lecture, we discussed the procedure of unitization of C-star algebras, and we have seen that there are two different ways of defining a norm, a C-star norm on the unitization. The construction depends on whether or not the algebra is unital. If it is unital, then the norm on the unitization is given by an explicit formula, which involves a direct sum decomposition of a class into a direct sum of two ideals. And if it is not unital, then the formula is completely different. It is kind of the C-star norm on the unitization is a kind of operator norm, the norm of the multiplication operator, which acts on the algebra A. So the constructions, the two constructions are different, but corollary 2 shows that actually the norm, the C-star norm, the norm on the unitization of A, which makes into a C-star algebra, is unique. And it is always given by this formula. The second statement, this equivalent form of corollary 2, can also be extended as follows. Corollary 3. Suppose that A is a Banach star algebra, and B is a C-star algebra. I claim that every star homomorphism phi from A to B is automatically continuous, and moreover, the norm of phi is less than or equal to 1. So this is another automatic continuity result. So some time ago we proved that every character of a Banach algebra is automatically continuous and has this property. And now we will show the same property for star homomorphisms from the Banach star algebra to a C-star algebra. Again, let's start with a self-adjoint element of A. For every self-adjoint element A of A, the element phi of A is also self-adjoint, because phi is a star homomorphism. And so its norm, the norm of phi of A, is equal to the spectral radius of phi of A. Because B is this is an element in B, and B is a C-star algebra. But any homomorphism between algebras reduces the spectral radius. We always have this inequality because phi reduces the spectrum. Well, formally, we proved that phi reduces the spectrum in the unital case, where phi is a unital homomorphism between unital algebras. But if it is not unital and the algebras are not unital, we can simply join the identities to A and B. We already know that the unitization of C-star algebra is a C-star algebra. So anyway, we see that phi reduces the spectrum, so it reduces the spectral radius. We have this inequality. And the spectral radius of A is less than or equal to the norm of A. So we see that the norm of phi of A is less than or equal to the norm of A, if A is self-adjoint. And if we now take an arbitrary element of A, then we apply the same trick to A star A, which is self-adjoint. So by the C star axiom in B, we see that the norm of phi of A squared is equal to the norm of phi of A star phi of A, which is equal to the norm of phi applied to A star A. Phi is a star homomorphism. A star A is self-adjoint. This one is self-adjoint. And for self-adjoint elements, we already have this inequality. And the norm of this element is less than or equal to the norm of A squared. And this completes the proof. So we see that the norm of phi of A is less than or equal to the norm of A. Okay, so let's now look at not only at the spectral radius, let's now look at the spectrum itself. Theorem 2, and this is another fundamental spectral property of C-star algebras. It states that if A is a C-star algebra, and little a is a self-adjoint element of A, then the spectrum of A is real. The spectrum of A is real. Well, we don't assume that A is unital, so we must take the non-unital spectrum here. But of course, if A is unital, I can remove the prime, because let's recall that in the unital case, the only difference between the spectrum and the non-unital spectrum is 0, which is of course real. So the spectrum of a self-adjoint element is real. By the way, this once again, this emphasizes an analogy between self-adjoint elements and real numbers. So the spectrum of a self-adjoint element is real. To prove this result, we may assume from the very beginning that the algebra A is unital. We may assume that A is unital, because if it is not unital, then we consider the unitization, which is also a C-star algebra. So let's take a point lambda in the spectrum of A. So let's write it in the form alpha plus I beta, where alpha and beta are real numbers. So we want to show that lambda is real, that is, we want to show that beta equals 0. The trick is the following. We observe that for every real number t, the element lambda plus it belongs to the spectrum of A plus it1, just by the spectral mapping theorem. So the absolute value of this number, lambda plus it, is less than or equal to the norm of A plus it1. For convenience, we take the square here and here. So what is the left-hand side, since lambda was written in this form? So the left-hand side is the sum of two squares, the square of the real part and the square of the imaginary part. So the real part is alpha squared, and the imaginary part is t plus beta. T plus beta squared. So this is equal to alpha squared plus t squared plus 2t beta plus beta squared. As for the right-hand side of this inequality, we can calculate it by using the C-star axiom. So by the C-star axiom, this is equal to the norm of A minus IT1. This is the adjoint of this element, times A plus IT1. Here we use the assumption that A is self-adjoint. What is this? This is nothing but A squared plus T squared 1. And by triangle inequality, this is less than or equal to the norm of A squared plus T squared. So this number is less than or equal to this one for every t. So we cancel t squared from here and from here. And we deduce that alpha squared plus beta squared plus 2 beta t is less than or equal to the norm of I squared. And this is true for every real number t. So t was arbitrary. So this affine function, whose graph looks like this, or maybe like this, is bounded from above by this number, which is possible if and only if this coefficient is 0. So we deduce that beta is 0. And this is exactly what we wanted to prove. So this means that lambda is real. Okay. In fact, there is a special name for star algebras which satisfy this property. They are called remission algebras. By definition, star algebra A is called remission if the spectrum of every self-adjoint element of A is real. So theorem 2 implies that every C-star algebra is a Hermitian. So all C-star algebras are Hermitian. And more generally, every spectral invariant star subalgebra subalgebra of a C-star algebra is Hermitian, because the spectrum, if it is spectral invariant, then the spectrum calculated with respect to the subalgebra is equal to the spectrum calculated with respect to the bigger C-star algebra, and so it is real. For example, the algebra of one times continuously differentiable functions on an interval is Hermitian because it is a spectral invariant subalgebra in the algebra of continuous functions.
В пункте 2 смысл заводящих квадратов не хватает самости до цезута алгебры, да?
Да.
Все.
Да. Если она была замкнута, она была обсервация. Но она обязательно замкнута. Вот. This one is not closed in CFAB, so it is not a C-star algebra. And in fact, by the way, there will be an exercise in our next exercise sheet, which states that we cannot introduce any norm on this algebra and there is no involution actually on this algebra, and there is no norm on this algebra, which make it algebra itself into system algebra. So it is never a system algebra with respect to any norm and any involution. But it is involution because it is spectrally invariant in C of AB. By the way, a useful exercise. We have another canonical example of a Banach star algebra, which is not a C-star algebra, the disk algebra. So the question is it Hermitian or not? It is a Banach star algebra. So it's natural to ask whether or not it is Hermitian. And by the way, a little announcement, we will see soon, not today, but maybe at the next lecture, that all L1 algebras associated to locally compact Wheeler groups are Hermitian. Okay, the following proposition gives a useful property of Hermitian algebras. The proposition: if A is an Hermitian star algebra, then all characters of A are star characters. That is, they preserve the evolution. To prove this result, we first of all would take a self-adjoint element of A. We know that the spectrum of A is real by assumption. The spectrum of A is real. Chi, if now chi is a character of A, so it is a homomorphism to the complex numbers. So it introduces the spectrum. So this implies that the spectrum of chi of A is also real. But this is the spectrum, the non-unital spectrum of a complex number. So this set consists of at most 2 points, namely chi of A itself and 0. So this implies that this means exactly that chi of A is real. So we see that chi takes self-adjoint elements to real numbers. And if we now take an arbitrary element in A, let's decompose A into the real and imaginary parts. So B and C are self-adjoint. And let's look at chi applied to A star. So A star is B minus IC. B minus IC. So we have chi of B minus I chi of C. But this is nothing but the complex conjugate to chi of B plus I chi of C. Because we already know that chi of B and chi of C are real because of this. So they are real. So this number is complex conjugate to this one, but this is nothing but chi of A. And that's it. So we see that chi preserves the evolution. In fact, for commutative Banach algebras, this property, for commutative Banach star algebras, this property characterizes the fact that A is Hermitian. So we have the following theorem. This is theorem 3. Suppose that A is a commutative Banach star algebra. Then the following conditions are equivalent. Condition 1, A is Hermitian. condition 2, all characters of A are star characters. Star characters. And property 3, the Gelfand transform of A is a star homomorphism. The Gelfand transform is a star homomorphism. That is, it preserves the evolution. And moreover, if these conditions are satisfied, if A is remission, then the range of the Gelfand transform is dense in the algebra of continuous and vanishing infinity functions. The image of gamma is dense. Well, we've just proved that 1 implies 2 for every irrational star algebra. This follows from the previous proposition. The implication 2 implies 3 readily follows from the definition of the Gelfand transform. Well, indeed, for every A in A, and for every character chi of A, well, let's look at the Gelfand transform of A star. So we want to show that this is the complex conjugate of the Gelfand transform of A. So we evaluate this function at chi. So by definition, this is chi evaluated at A star. But we assume that chi is a star character, so this is equal to chi of A complex conjugate. And this is nothing but A hat of chi complex conjugate. That is, in other words, this is the function A hat star evaluated at x at I. So we deduce that the Gelfand transform preserves the inversion. And to show that 3 implies 1, we take a self-adjoint element of A, and let's recall one of the fundamental properties of the Gelfand transform, which states that the spectrum, the non-unital spectrum of A, is equal to the range of the function A hat, or more exactly, the range of this function, and we also add 0 to this set. So this is true for every element in any commutative Banach algebra. But A was assumed to be self-adjoint, and we assume that gamma is a star homomorphism. So therefore the function A hat is real, and so this is a subset of the real line. And so we see that the spectrum of A is real, that is, the algebra A is Hermitian. So we now see that properties 1, 2, and 3 are equivalent. Now we have to show that the image of the Gelfand transform is dense. Why is it so? Well, let's now denote by B this image of the Gelfand transform. It is a subalgebra in C0 on the maximal spectrum. Let's now look at the unitization of B plus. So it sits in the unitization of C0 on the maximal spectrum. And let's recall that the unitization of this algebra can be identified with the algebra of continuous functions on the one-point compactification of the maximal spectrum. Which in turn can be identified with the set of all characters of A, including 0. Let's recall that this is our notation for the set of all characters of A. So this is the unitization of this algebra. So B plus is a unit of subalgebra of this one. And we can easily see that this subalgebra satisfies all the conditions of the Stolz-Weierstrass theorem. Subalgebra satisfies the conditions of the Stolz-Weierstrass theorem. Well, indeed, it's a unit of star subalgebra. B plus is a unit of star subalgebra. In this algebra, it is a star subalgebra because we already know that gamma preserves the involution, so it is a star subalgebra, and it clearly separates the points for some trivial reasons. If you have two different characters, we can always find an element in A where these characters are different at this point, and this means precisely that B plus separates the points of this algebra. So it satisfies the conditions of the Stolz-Weierstrass theorem, and so it is dense. B plus is dense in the algebra of continuous functions on A hat plus. And now it's a simple exercise to deduce that this density implies that B is dense in C0 on the maximal spectrum. Well, basically the exercise is that if B is contained in C and B plus is dense in C plus, then B is dense in C. This is rather easy. Okay, now we are ready to prove the Gelfand-Marburg theorem, the commutative Gelfand-Marburg theorem. Which states that if A is a commutative C-star algebra, then the Gelfand transform is an isometric star isomorphism. Isometric star isomorphism. So as a corollary, every commutative C-star algebra is actually isomorphic to the algebra C0 of X on a locally compact Hausdorff space X. Well, we already know that A is a Hermitian, so gamma is a star homomorphism, and the previous proposition, the previous theorems shows that the image of gamma is dense. So we already know that gamma is a star homomorphism, and the image of gamma is dense. So to complete the proof, we have to show that it is isometric. So we have to show that gamma is isometric. And this will be the end of the proof, because an isometric map between bound spaces has a closed image. So its image is dense, it is closed, and so it is surjective. So the surjectivity will follow from the fact that gamma is isometric and has a dense image. Why is it isometric? This is basically the same argument as in the proof of, let's look at the respective result. The argument will be essentially the same as here. More exactly, we start with a self-adjoint element. So for every self-adjoint element of A, the norm of gamma of A. So we know that this norm is equal to the spectral radius of A. This is true for every commutative Banach algebra. But the spectral radius of A is equal to the norm of A, because A was assumed to be self-adjoint. So gamma is isometrical on self-adjoint elements. And now if we take an arbitrary element of A, we use the C star axiom. So on the one hand, this algebra is definitely C star algebra. So the norm of gamma of A squared is equal to the norm of gamma of A star gamma of A. But gamma is a star homomorphism, so this is equal to the norm of gamma applied to A star A. But the element A star A is self-adjoint, and we already know that gamma is isometric on self-adjoint elements, so this is equal to the norm of A star A. But A is also a C star algebra, so this is equal to the norm of A squared. So we look here, and deduce that gamma is isometric. And this completes the proof. So in summary, gamma is an isometric star isomorphism. Let's now briefly discuss a category theoretic interpretation of the Gelfand-Nalmec theorem. A category theoretic interpretation. Let's recall the following general category theoretic definition. You will have two categories A and B. Two categories. And a functor, a covariant functor from F from A to B. Covariant functor. Then we say that F is an equivalence. F is equivalence between A and B. If there is another functor, covariant functor G, which acts in the opposite direction from B to A, such that GF is isomorphic as a functor, is naturally isomorphic to the identity functor on A, and Fg is isomorphic to the identity functor on B. And this functor G is usually called a quasi-inverse of F. Quasi-inverse of F. It's easy to show that if it exists, then it is unique up to a natural isomorphism. So let's now look at two concrete categories. One of them is the category of compact Hausdorff spaces, and another one will be denoted. So we should use the following notation. Denoted by C U C star, the category of commutative unital C star algebras. The category of commutative unital C star algebras. So objects of this category are just commutative unital C star algebras, and morphisms are unital star homomorphisms. Unital star homomorphisms. So we have two functors. One functor acts from the category of compact Hausdorff spaces to the category of commutative unital sister algebras. Actually, we have already considered this functor before. It takes every compact Hausdorff space to the algebra of continuous functions in this space. And we have another functor which acts in the opposite direction, and this is the maximal spectrum. So these functors are contravariant. To make them covariant, we take the opposite category here. So we formally invert all the arrows in the category of compact Hausdorff spaces. And so now our two functors are covariant. And the Eagle-Van-Dijk theorem, this is a category theoretic form of the Eagle-Van-Dijk theorem, states that these two functors are equivalences of categories. Are equivalences of these two categories. And more exactly, they are quasi-inverse to each other, and the respective isomorphisms are very concrete. Moreover, if we compose them, if we take first take the apply C and then apply max, then this composition is isomorphic to the identity functor of compact Hausdorff spaces, and the isomorphism is our map epsilon, which was discussed some time ago. This is the canonical isomorphism between a compact Hausdorff space and the maximal spectrum of C of X. So it takes every point in X to the respective evaluation character. And if you compose these functors as follows, first we apply max and then we apply C, then this functor is isomorphic to the identity functor of the category of commutative unital sister algebras, and the isomorphism is nothing but the Eagle-Van transform. So in the general case, let's recall that in the general case, that is, if we consider the bigger category of commutative unital Banach algebras, then the Eagle-Van transform is a natural transformation, a natural morphism from this functor to this one. But for sister algebras, this is an isomorphism. So this is a category theoretic form of the Eagle-Van theorem, that is in the unital case. Actually, it can be extended also to the non-unital case, but there are some technical details here. The details are in the definition of morphisms, so we have to define morphisms between commutative non-unital sister algebras and between locally compact spaces in an suitable way. If we do it, then we get a non-unital version of this result. But in the unital case, it is especially transparent. Actually, this result is a classical example of a complete duality between algebra and geometry, algebra and topology. So this category is essentially algebraic, the category of commutative unital sister algebras, and this is a purely topological category, and they are equivalent. Another classical example of such a duality between algebra and geometry is a category theoretic form of Hilbert's Nullstellensatz, which implies that we have a similar duality between the category of affine algebraic varieties over the complex numbers and the category of commutative unital finitely generated algebras without nilpotence. Results of this form lead naturally to non-commutative geometry, which is in fact not a theory, but rather a philosophy which contains of several branches, namely non-commutative algebraic geometry, non-commutative differential geometry, non-commutative topology, and so on. So from this point of view, the theory of system algebras is often interpreted as non-commutative topology. And an arbitrary non-commutative unital system algebra can be interpreted as the algebra of continuous functions on a non-commutative compact topological space, which of course doesn't exist. So this paradoxical point of view rather unexpectedly leads to a very deep and fruitful theory, which has many connections with other fields of mathematics. And it turns out that sometimes some pure topological constructions may be considered as a special case of a similar construction in the category of non-commutative system algebras. That is, has many constructions in topology have natural non-commutative analogs. For example, a classical example of such generalization is K-theory. It turns out that K-theory of compact topological spaces can be completely embedded into K-theory of system algebras, which is quite useful. By the way, there will be another course in the next term, which will be completely devoted to K-theory of system algebras. Okay, so that's all I wanted to tell you about the Gliffman-Dynamic theorem. Now our next goal is to apply this theory, the theory of commutative Banach algebras, to commutative harmonic analysis. So our next goal is to introduce the Fourier transform. Fourier transform. On locally compact abelian groups. So suppose the G is a locally compact abelian group. And as usual, for convenience, we assume that G is second countable. This is our standard assumption, which simplifies some technical measure theoretic points. In particular, we can easily consider 1 of G, the group algebra 1 of G, and the measure algebra M of G. Original by G hat, the set of all continuous unitary characters, that is, all continuous homomorphisms from G to the circle. G hat is clearly an abelian group under pointwise multiplication. An abelian group under the pointwise multiplication. And we say that G is the dual group of G. G hat is the dual of G.
Можно помнить, вот условие второй аксиомы счета, если мы просто хотим, чтобы наша мера Хара была вот, просто эквивалентом, что на компактной, конечно. Что если вот оно вторая аксиома счетности, то мера Хара, она эквивалент тому, что она просто на компактной, конечно.
Нет, мера Хара, она всегда конечна на компактных.
Нет, в смысле, там же еще есть два условия, что она внешняя и внутренняя.
Да.
И вот мы как раз требуем, чтобы вот просто не думать об этом.
Да, не только. Не только. So why do you assume that G is second countable? For example, some time ago when we discussed L1 of G and some related stuff, first of all, we can freely use Fubini, the Fubini theorem. Because classically, the Fubini theorem is only about sigma finite measures, and if G is not sigma compact, then the Hard measure is not sigma finite, and to use linear theory, we must always look at some special sigma compact sets where our functions are concentrated. This is one of the technical points here. Another technical point is that in the non-sigma compact case, the dual of L1 is not the classical L infinity. It can be interpreted as a kind of L infinity space, but it has to be redefined in a suitable way. This is another point. Also, when we defined product measures, and this was essential in our approach to convolutions, the usual product measure on G cross G is not defined on all Borel sets. It is defined only on the sigma algebra generated by products of Borel sets, or on so-called Borel rectangles. But in general, if G is not second countable, then this sigma algebra is strictly smaller than the Borel sigma algebra on G cross G, which is not very good, because we want to consider products. We want to consider the product measure of the Hard measure by itself, and it has to be the Hard measure on the product. But in general, it is defined on the smaller sigma algebra. We have to do something with this case. So in order to in each of these cases, we can overcome this difficulty, but it requires some special measure of theoretic arguments. So just to save time and just to forget about such technicalities, we assume from the very beginning that G is second countable. So this essentially simplifies our arguments. Okay, so G hat is said to be the dual of G. This is the dual of G. So there is also an abelian group. And let's now introduce a canonical topology on G hat. We define the Petrarchan topology on G hat is defined to be the restriction to G hat of the compact open topology on the space of continuous functions on G. Or the compact open topology on C of G. Actually, we have already discussed this construction when we defined the dual group of the integers of the real line and of the circle at the second lecture. So in the general case, the definition is exactly the same. We equip C of G with the compact open topology, and we consider the induced topology on G hat. So let's recall how the standard base of this topology looks like. If chi is a character of G, so an element of G hat, K is a compact subset of G, and epsilon is a positive number, then we denote by U K epsilon of chi the set of all characters phi of G such that the seminorm of phi minus chi associated to K, so this number is less than epsilon, where the respective seminorm is just the supremum over K. So So this is, if we consider all compact subsets of G, then we get a family of semi-norms on C of G. This family determines topology on C of G, and the induced topology is the Pontryagin topology on G hat. And all sets of this form, if we fix chi and consider all k and all epsilon, we get the standard base of open neighborhoods of chi. K epsilon of chi, where k runs over the family of all compact subsets of G, and epsilon over all positive numbers. So this is the base of open neighborhoods of chi. In fact, I'm cheating a bit here, because in the general case, you probably remember that in a general case, when we generate the topology by a family of semi-norms, such sets form a subbase of neighborhoods. But in this case, this is not just a subbase, but it's actually a base, because if we take the intersection of two sets of this form, say k1 and epsilon 1, and intersect it with the respective neighborhood uk2 epsilon 2 of chi, then such an intersection clearly contains uk epsilon of chi, where k is the union of k1 and k2, and epsilon is, for example, the minimum of epsilon 1 and epsilon 2. And so this inclusion really implies that this is indeed a base of neighborhoods, but not only a subbase. It's this family. This base, and not only a subbase. Neighborhoods of chi. Okay, so now I claim that if we equip G hat with the Pontryagin topology, then we get a topological group. G hat is a topological group. The proof is quite straightforward. Well, actually, I'll give you a sketch of proof, but I hope you will easily recover all the details. If we take two characters, say chi1 and chi2, and look at their neighborhoods of the following form, and take their product, then this product will be contained in the following neighborhood of chi1, chi2. So we keep k and replace epsilon by 2 epsilon. This is a little calculation, a simple exercise for you. Just use the triangle inequality. And this implies that the multiplication is continuous. Because if we start with chi1 and chi2 and take basic open neighborhood of their product, then so we get two neighborhoods of chi1 and chi2 such that their product is contained in here. So this implies that the multiplication is continuous. The multiplication on G hat is continuous. And also have to show that the inversion map is continuous. And this is also very easy because of the following equality. And this is also an easy, a simple exercise. here the hint is that chi is a unitary character, so chi inverse is nothing but chi complex conjugate. And this equality originally implies that the map which takes chi to chi inverse is continuous. So it is a topological group. We will see soon at the next lecture that this group is locally compact. But at this point, this is not entirely obvious. Anyway, we already know that this is a topological group. Let's now introduce the Fourier transform. When we discussed the Fourier transform on finite abelian groups, on the integers, on the circle, and on the real line, we always consider the Fourier transform of integrable functions. But for technical reasons, it would be more convenient to give this definition in the more general setting and to define the Fourier transform of complex random measures. So the definition looks as follows. The Fourier transform of a complex random measure, mu, is a function mu hat of the dual group given by the following simple formula. Mu hat evaluated at the character chi is just the integral of chi over mu of chi with respect to mu. Come. Not f but chi. So shortly we can shortly write this as follows. So we have used this notation some time ago when we spoke about complex measures. So it's simply the integration of chi against mu. In a special case where our measure is comes from an integrable function, we get the definition of the Fourier transform of an integrable function. So more exactly, we take our measure mu on G, and by using this measure, we consider the embedding of L1 of G into the measure algebra M of G, which takes every function f to the measure f mu. So we already know that this is an isometric star embedding of L1 of G onto a closed two-sided ideal of M of G. And we define the Fourier transform of f, the Fourier transform of an integrable function f on G is just the Fourier transform of the respective measure. So explicitly, this function is given by the following formula. F hat of chi is the integral of f chi g mu. Okay, so what can we say about this function f hat, or more generally mu hat? Let's observe that this function is bounded. Well, indeed, mu hat evaluated at chi. So the absolute value of this integral can be estimated as the integral of the absolute value against the variation of nu. But chi is unitary, so this is 1. And this is nothing but the norm of mu, the norm of nu. So as a result, we deduce that mu hat is bounded And moreover, the uniform norm of nu hat is less than or equal to the norm of nu. But in fact, this function is not only bounded, it is also continuous. Nu hat is a continuous bounded function on G hat. Well, why is it so? Let's take a point in G hat, a character, say chi 0. And let epsilon be a positive number. Then, by using the regularity of nu, we can always find a compact subset, compact set K from G, such that the variation of nu is less than epsilon over G minus K. This is because the measure is regular. If I now take a character chi in the respective neighborhood of chi 0, K epsilon of chi 0, and if we look at the following number, nu hat at chi minus nu hat at chi 0, so what's that? This is this can be estimated as the integral of chi minus chi 0 with respect to the variation of nu, just by the usual properties of the integral. So let's split this integral into two pieces, namely the first piece will be over k, and the second one over G minus k. When we integrate over k, this function chi minus k0, if we recall the definition of the respective neighborhood, where is it? So this is the definition of the respective neighborhood. We see that everywhere over k, chi minus k0 is less than epsilon. So the first summand is less than or equal to the less than or equal to epsilon times times the norm of nu. And the second summand can be estimated as follows. In any case, this difference is at most 2, because the characters are unitary. So this is at most 2 times the measure of G minus k. But the measure of G minus k is less than epsilon. So the second summand is less than 2 epsilon. So in summary, we see that this is a constant times epsilon. And this happens for every point chi in the respective neighborhood of chi 0. So therefore, this implies that nu hat is continuous. And this completes the proof. So as a result, this is the last line for today. We can introduce the following notation. We denote by script f the map from the measure algebra of G to the algebra of continuous bounded functions on G hat G, which takes every function, every measure nu to the Fourier transform nu hat. And we say that script f is the Fourier transform on G. So let's observe that since the norm of nu hat is less than or equal to the norm of nu, f is a bounded linear map. So the linearity is clear, and this inequality, or to the respective inequality, this inequality means implies that f is bounded. So it is a bounded linear map. Okay, so that's all for today. At the next lecture, we will see that this map is actually a unital star homomorphism between these two Banach star algebras. And we'll see that if we restrict the Fourier transform to L1 of G, so we will be mostly interested in the Fourier transform on the algebra L1 of G, then it can be identified with the Gelfand transform of this algebra, and in particular G hat can be identified with the spectrum of L1 of G. So this result enables us to apply methods of commutative Banach algebras in harmonic analysis.